Okay, now here we have a force displacement graph. Okay, so I want to write it down here. This is a force versus displacement. Force versus displacement graph. The area under force displacement graph is work done. Okay, because you look at the formula is work done equal to force times displacement. Force times displacement. So that's why area under force displacement graph is the work done. Okay, or if we want to write integration, work done is actually integrate F versus S. Okay, integration we get area under the force displacement graph. Okay, last time in previous chapter we learned about impulse, isn't it? Okay, impulse. Okay, here you see. This one is a force versus time graph. Force versus time graph. The area under the graph. Just want to write it here. The area under this one is what? It's called impulse. Is the impulse, yeah, or the symbol J. Symbol J. It is the area under force time graph. If force displacement, the area is work done. If force time, okay, remember, see the difference. This one is displacement, this one is time. Different. If force time is impulse, okay, or the formula is impulse is actually integrate the force versus time graph. Yeah. Actually, you remember this simply work done is force time displacement, isn't it? But for impulse, it is force time, isn't it? One is force displacement, one is force time. Okay, so you must look at carefully, yeah, on this one, yeah, this one. If displacement, it is work done. If time, it is a impulse. So don't get it wrongly, yeah. So if, like, let's say this force is let's say this is 10 Newton, force 10 Newton, and displacement over 10 Newton. So Newton, okay, and this displacement is let's say 20 meter. So how to get the area under the graph? To get the work done. So the work done is actually the triangle, yeah, half times this is 10 Newton, isn't it? So times 10 times 20 meter, yeah, 10 Newton, 20 meter. So what do you get? You get 100 joule of work done. That's the area under the graph. Okay, hope you understand. Force time, this is force displacement. This is force time. Force displacement area is work done. Force time area is impulse. Impulse is the change of momentum. Yeah, impulse is actually change of momentum, or we can say final momentum minus initial momentum, or mv minus mu. This is the previous chapter. Okay, so now let's look at this total work done, yeah, or net work done for multiple forces. So net work done or total work done, we can write it as net work done or total work done is the sigma work done, or we sometimes can write as a total, total work done, or we also can write it as a net work done, N-E-T-T, net. Yeah. Okay, we write it carefully, N-E-T-T, net. Right. So let's look. So this is total work done, or net work done, or sigma W. Means total work done. Okay. Yep. Okay, look at here. So we have two methods to find the total work done. Yeah. Let's say now a block is acted by not just one force, but multiple forces. All right. Let's say now the object is not is acted by multiple forces, not just one force. You have here, like, see here, let's say you have three forces. You have F1, you have F2, you have F3, all acted on the same objects. So what is the total work done? Okay, by all these forces. We know that each forces have their own work done. Yeah, like force F1 have W work done 1. Okay, work done 1. F2 has work done 2. F3 has work done 3. Why we have multiple forces? Why we have multiple forces? Because, like, for example, like an object, we do draw a free body diagram, isn't it? We did draw a we did draw a free body diagram, and an object is not acted only by one force. It has multiple forces. For example, let's say you like this one, you have an external force. This is maybe it's a pulling force. Okay, this is a pulling force by a human. A human pull this object to the right. Okay, so this is the pulling force, and the object also has the own weight, gravitational force, weight. We don't write as W, but we write as Fg, because W seems like work done, isn't it? So we don't want redundant alphabet. We just put as Fg. Yeah, and then it also has the normal force. Normal force. It also has friction if the surface is rough. So an object easily you have multiple forces. You won't have only one force. You won't have only one force. You have multiple forces acting on the same object. So what is the total work done by all these forces? Okay, how to find? There are two methods to find it. Yeah, so that's why here I put it. There are two methods. Yeah, here you have method 1, and then we have this is method 1. And this is method 2. I'm going to show you what is these two methods. How going to do these two methods? How to find the total work done? There are two methods to find the total work done. Okay, how are we going to do it? Okay, let's look at these two methods. Okay, our first method is find work done of individual force first. Find the work done of individual force. Okay, like F1 has work done 1, F2 has work done 2, F3 has work done 3. Okay, so first of all, before we find the total work done, we find the work done of each forces. Okay, this one is very small. Okay, I make it bigger. Like work done F1. Okay, so find the work done of the F1, which is F1, yeah, work done F1. You see that as subscript, I put F1 or work done F1. It is using if our force is F1, then it is F1 multiply displacement. If it is F2, then we use the F2 multiply displacement. If the force is F3, then we use F3 to multiply displacement. Okay, so okay, for F1, then we write the subscript for work done as WF1. WF1, then the force is F1 dot displacement. Okay, so this one become F1 as cos theta. Of course, this one, the theta also theta for F1. Yeah, this one put as theta 1. Yeah, we can consider the theta is over here. This is the theta. This is the theta 1. Understand? This is the theta 1. Theta 1 is between F1 with displacement. Okay. And then, how about the F2? F2, work done F2 is F2 dot displacement. So F2, force F2 multiply this displacement, and then cosine theta 2. This one use theta 2. So the angle theta. So always compare with displacement. Displacement is the most important. So theta 2 is okay, not this one. Theta 2 is we compare F2 with displacement, so which is this one, 180 degree. Understand? This is theta 2, yeah, which is this is the theta 2. Okay, so we just put cos 180 later on. Okay, yeah, angle between F2, between F2 and displacement. So the angle between them is this theta 2, 180. Okay, and then how about the F3? F3, work done F3. You compare F3 F3 with displacement. So okay, round off this angle. So where does F3? So work done F3 is F3 dot displacement. So F3 displacement cos theta 3. So we put that as theta 3. So where is the theta 3? Where is the theta 3? Theta 3 is we compare F3 with displacement. So this is the theta 3. This is the theta 3. Theta 3. And seems that this is 90 degree right angle triangle, right angle perpendicular. F3 in displacement is 90 degree. So this is theta 3. Later we just cos 90. Understand? Cos 90. This is theta 3. Okay? So we need to find the work done of each one. Okay? Get this work done F1, work done F2, work done F3. Later on, we just substitute into each work done. We substitute into here. We substitute into here. And then we total up. We total up all the work done. We get the net work done. This net work done also we can write as what? We can write as sigma W also. Yeah. Or we can write as total work done. So we find the work done of each forces. Yeah, identify their individual angle theta 1, theta 2, theta 3 by comparing between individual force with the displacement. Important thing is displacement. We always need the displacement to compare. Yeah, to compare our forces. So find work done for each forces. And then we total up all the work done, WF1 plus WF2 plus WF3. Then we get the total work done. That is the first method. Okay, let us find out how to find. Let's say I have one conditions, like you see this one, method 1. Okay, let's say I have this pulling force at 60 degree to the displacement. Pulling force to the right. And then we have the weight, the normal force, the friction. We have friction because this surface is rough. Okay, because provide the mu k value. So how to find the total work done? How to find the total work done? So first thing is you must find the work done for each forces. Work done for each forces. Then only you can find the total work done. Okay, so find work done for each forces. So important thing is you must always draw the displacement first. You must always draw the displacement direction because we need for chapter 5, you need for this chapter work energy power, you need to draw the displacement because we always compare the force with displacement. Yeah. So okay, never mind. Look at here first. So look at this one. So how to find the work done? Let's say for external force. So we need to find work done for each first. That means okay, let us do it now. Okay, so we need to find the work done of the external force. So how many work done we have here? We have 4 forces, means we have 4 work done. We have the work done for external force. We have the work done for, then we have work done for normal force. Then we have work done for the gravitational force. We can write as Fg, yeah. Work done for gravitational force, and then work done for friction. Work done for friction. Okay, so okay, maybe over here. Okay, so now let's find the work done for external force. Work done for external force, it is equal to we just use the external force dot with the displacement. So this one is external force as cosine what angle? Force times displacement cosine what angle? So remember, always compare with displacement. Displacement you need to draw beside the object like this. Draw your displacement just beside the object. Yeah, you must draw the displacement, not just draw the forces. Not just draw the forces, you must draw the displacement beside the object so that you can get the angle, so that you can compare your direction of force. You can compare each forces with the displacement. Okay, So you must draw the displacement, so then only we can compare the angle between force and displacement to get the angle. Understand? That's why for this chapter, chapter work energy power, you need to draw displacement. In short, what I can say is maybe again I want to show you this one. Okay, look at this one. In previous chapter, we learned about forces. We also draw free body diagram. Okay, we think all the object as a point mass. Okay, this is a point mass. You need to draw a point at the center of the object. Okay, so for forces, we are using the formula of total F equal to ma. So the importance is about the acceleration, isn't it? And then that's why for this for chapter forces, we need to draw direction of acceleration. We need to draw the direction of acceleration. Then only we can know which forces is positive and which forces is negative. Like same direction with acceleration, we put as positive force. If opposite the acceleration, we negative force. So we draw the acceleration. We draw the acceleration to compare our forces with acceleration. Same direction with acceleration, positive force. Opposite the acceleration, negative force. Newton's second law, isn't it? So for chapter forces, the free body diagram must have acceleration. And then now in this chapter, work done. When talking about work done, we use the formula of work done equal to let's say work done force. We use the force times displacement cos theta. So for work done, our importance is about the displacement. Do you see that? Our importance, our emphasis is on displacement. We need to compare. We need to compare between force and displacement. We need to compare between these two to get the value of angle, get the value of theta, because the theta is between force and displacement. So for this, the free body diagram for work done, for this part work done, we need to include the displacement direction. We need to include the displacement direction, not the acceleration. Understand or not? Not the acceleration, is the displacement. What we need the displacement so that we can compare our force, with displacement to get the angle theta. Understand or not? So for this chapter, for work done, we need the displacement. We need to draw the displacement in our free body diagram. Yeah, just beside the object. Don't draw on the object. Don't draw on the object. Draw on just beside the object so that we can compare each force with the displacement to get the angle theta. And then later on this chapter, further down, we learn about power. Power, the formula is almost the same like work done. Okay, later you will learn about power. Like say power, let's say power by external force. Okay, power by external. Each of these forces also have their own power. We have power by external force. We have power by normal force. Power by friction. Power by gravitational force. Okay. In the last video, I will explain about this power. You see that? Power also have power by external force, power by gravitational force, power by normal force, power by friction. Just like the work done has work done by external force, work done by gravity, work done by normal force, work done by friction. So the difference is for work done, we draw displacement. For power, we draw velocity because we compare with all velocity. Do you see that? We compare all with velocity. This work done, we compare with displacement. So the difference is power use velocity. Power use velocity. Work done use displacement. In later video, I will explain about this. So for this one, for free body diagram for power, we need to draw velocity. Velocity over here. So this is our importance, because why our velocity is important? Because our formula has velocity. The formula for power is Fv cos theta. Our V is very important. Velocity is important because we need to compare each force with velocity to get the value of theta. Okay, so for power we need to draw velocity. Okay, for work done we need to draw displacement. For forces we draw acceleration to get positive force or negative force. Okay, all right, good. Now let's continue. Yeah, let's continue our business here. Okay, so remember for work done, our free body diagram must have displacement. Okay, displacement. Now, okay, just now I'm talking about the external force. This external force is 60 degree. Compare now, work done for external force. Work done for external force. We compare external force with displacement. So displacement is to the right. Force is 60 degree from displacement. So this is cos 60. This is cos 60 degree. Understand? So we can get the value of this work done by external force. Now how about the work done by gravitational force? Work done by gravitational force, we use gravitational force dot with displacement. Dot with displacement. So we got the Fg is actually mg because it's the weight. Yeah, gravitational force is actually the weight. But we don't write as W because W looks like work done, not as look like work done, look like weight. So we don't want to confuse both of them. We just write as gravitational force. Yeah, mg. Yeah, or Fg we just substitute with mg and then multiply with the s. Okay, s. This one s is displacement, and then cosine what? So you see, you compare the gravitational force with displacement. Displacement to the right, gravitational force downward. So it's 90 degree. Gravitational force is 90 degree to the displacement. So this one we cosine 90. This one we cosine 90. Understand? Yeah, but of course, anything cosine 90, you get 0. Yeah, later on this work done, we get 0. Like this one work done, you get a positive value. Yeah, cosine 60, you get a positive value. Okay, how about the work done by normal force? Then this work done by normal force, we multiply. We multiply the normal force with dot with displacement. So this one become ns cosine. Yeah, normal force times displacement cosine. This normal force also 90 degree to the displacement. Always compare with displacement. So this one also 90 degree. Again, this one cosine 90, you get 0. You get 0. 0 work done. How about the friction? Friction, if work done by friction, you compare friction with the displacement. So this one you compare work done by compare the friction with displacement. So this one is a friction times displacement cosine. So the friction and displacement, they are opposite, isn't it? Opposite, that means 180 degree. 180 degree is 180 degree. So this is cosine. You get this one cosine 180. Usually you get this one actually is in a value of -1. Usually get a negative value, negative work done here. This -1. So once you got work done for each forces, yeah, work done for each forces, then you total work done. To find the total work done, we continue. We write here. So the total work done, or we can write as the net work done. The net work done is work done by external force plus work done by gravitational force plus work done by normal force and work done by friction. Then we total up, we get the total work done. Understand? Then we get the total work done. Understand or not? Compare each forces with the displacement to get their respective angle. Then you can calculate, yeah, the work done. And then total all the work done, you get the total work done. That's method 1. The second method is we find the net force first. Because both method you will get the same answer for work done, for the total work done or the net work done. Yeah, both method. The second method is we find the net force first. This one we use back the previous chapter in the chapter forces. We use the total force equal to MA, that forces. We find the net force first. We find the net force, then we net force, we dot with displacement. Yeah, or net. So actually the net work done is actually using the net force. Yeah, because like just now, like you see here, we have 3 forces. 3 forces combined, you must have a net force. It is the net force dot with displacement to get the net work done. So it's a net force times displacement cos theta. So you need to find the net force first. Okay, our target is to find the net force. Then we compare with displacement and get the angle theta, and multiply, we get net force times displacement cos theta, you get the net work done. So how to do this this method? Okay, so this second method is we use back the previous chapter method. Previous chapter method. Okay, hold on a second, let me draw a line to separate these two. All right, okay, now the second method is, we like this one, we need to do x and y component first. We do x and y components, x component and y component. Find the force for each one. Like another line please. Okay, hold on a second. Yeah, you need to do okay, so look at here. So look at this one, we need to know this one, we need to find the direction of acceleration, because we use back the previous chapter method. F equal to ma. So the acceleration is, let's say, displacement to the right, so acceleration also should be to the right. Okay, so write the acceleration first. How should I draw? Acceleration to the right also. Okay, to the right. So acceleration to the right, so that means direction to the right is the force to the right is positive, force to the left is negative. Okay, like that. Okay, so the previous chapter, still remember how do you find the net force? How do you find the net force? Normally, if it is a horizontal surface, the acceleration is in the x component. Acceleration in the x component. So we use the total fx. Total fx equal to ma. Still remember? But our y component, because the block doesn't jump up and down, it just move in the horizontal direction, isn't it? So total fy normally is 0. Total the resultant force in y component is 0. So normally the resultant force is only in the x component. The net force is only the net force is only in the x component. So we find the net force in the x component. Then we use the formula net force dot displacement fs cos theta. Then we can find the net work done straight away. Okay, so like you see this one, okay, like okay, for example, like this one, maybe you can do, okay, maybe I do it up for you. Like this one, how to get the net force for in x component. Maybe I do it up for you. Like this one, you have two components. Remember, resolve first your vector. You have you see this one, this net force, this external force. This external force has two components. It has x component and y component, isn't it? And y component. So it has two components. This one is yeah, maybe make it bigger. This one is external force cosine 60. This one is okay, this one is f sine 60. This one f cos 60 because adjacent to 60, isn't it? Adjacent to 60. F sine y component, the y component is f sine 60. F sine 60 because it's opposite to 60. Okay. So look at the x component. We have two forces. We have f cos 60 and the friction, isn't it? So which forces should be positive? F cos 60 should be positive because that's why you need to draw acceleration. For method 2, method 2 you need to draw acceleration because we need to know which force is positive and which force is negative. Which force same direction with acceleration, that will be positive. Which force opposite the acceleration, that will be negative. Understand or not? So like for x component here, okay, x component here is f cos 60 is positive because same direction with acceleration. That is f cos 60 positive. Okay, and then the friction is negative because opposite the acceleration. That will put negative friction. Negative friction. Negative friction. Then that will be equal to ma. But this question no need to find acceleration because actually we just want the net force. This is actually the net force already. net force, yeah, or we can say the actually we no need to write yeah, this is the net force, yeah, we just write total F, yeah, this is the net force. So our net force actually is okay, this is net force. How about the y component? Look at the y component. Look at the y component. Y component has what? N f sine 60 fg, but no acceleration, isn't it? So we just put a direction going upward positive, going down negative. But the net force is not in the y component. Maybe I can write it out for you also. I can write it out. This one you can write as this one is going up is positive, going down is negative, going down is negative. Yeah, is mg lah. Fg is mg, go to 0. But the net force is not in the y component. The net force is not in the y component, so we disregard lah. But we need to find the normal force also. Yeah, for this one, we need to do this one also to find out the normal force later on. We need the normal force later on to substitute to find the friction also. Because the friction, we need the normal force also, mu kn, isn't it? We need the normal force, okay, to find the friction also. But the thing is, our net force is only in the x component. You see that? Our net force is only in the x component, f cos 60. So you want the net force here. You want the net force here means is the x component, because the y component net force is 0. So we don't need this one. So we don't need this one. We only need this one. We only need this one. This part, x component. So our net force. So our net force here is actually our our resultant force, or our net force is only the resultant force in the x component, which is, so our net force, okay, our net force is actually f cos 60 minus friction. Once we get this value, the net force, okay, maybe we can draw it again. If it is a positive value, then if the object become like this, then we can draw so object, and this is the this the surface, okay. So our net force is in this direction. This is our net force. This is our net force. And draw the displacement also. Displacement is in this direction. Yeah, our displacement is to the right. Okay. So our net, very easy. Yeah, later on we want to find the net work done. Let's say our net work done will be equal to the net force. This net force. Okay, this net force with the displacement. Okay. Our net force dot with the displacement. So like this case, net force, displacement, what's the angle between them? Cos theta. Cos theta, the angle theta is the angle between the net force and the displacement, so it should be 0. This one should be 0. Okay, cos 0 is equal to 1. Yeah, cos 0 is equal to 1. So the answer, then we will get the answer. Okay, net force displacement cos 0. Okay. So there are two methods to find the net work done. Either you find the individual work done first, then you total all the work done, then get the net work done, or you find the net force first. You find the net force. Normally the net force is in the x component. Normally the net force is in the x component. From the x component there, but this is for horizontal surface. But for let's say the vertical, let's say the object is going downward, yeah, like lift, escalator. So that one will be y component. Okay, so it depends on questions. Like horizontal surface, normally the net force is in the x component. So you find the net force in the x component, that the net force in the x component, that is the net force. And the net force already in the x component. If the net force is already in the x component, so the theta normally become 0. Theta becomes 0. So you just net force times displacement, they get same work. Then you get the same total work done as the first method. Okay, so both method you will get the same value of net work done. Okay, so there are two methods for you to choose. total up the individual work done, or you just find the net force to find the net work done. Okay, that's all. Thank you.